let's go ahead and fill out this table, answer some questions. So for this first one, the integral from 1 to 4 of e to the negative x dx is definitely a definite integral because it's got limits of integration. Similarly, for this next one, the integral from 1 to infinity is also a definite integral. The next one isn't. Elizabeth and Jolene were just filling out this handout, which I will also post on Canvas if you would like to have a copy of it. So far we've said that this integral is definite. This integral is definite. This next integral is indefinite. So really, when you're thinking definite or indefinite, you're really just looking to see, are there limits of integration or not? So this one is for sure definite because it's the integral from 0 to 5. This one's definite. This one's indefinite. This one's definite. And this one's definite. Cool. On the other side here, we have whether it's proper or improper, or if that doesn't apply. So to be proper, the function has to be defined over the interval of integration. E to the negative x certainly is. So it's for sure on 1 to 4. It's for sure proper. And also the limits of integration have to be real numbers. So if the limits of integration have an infinity or a negative infinity, it's automatically an improper integral. So that one's for sure improper. And we don't talk about an integral being proper or improper if there aren't any limits of integration. So this indefinite integral is never proper or improper. Indefinite integrals are always just that language doesn't apply here. Not applicable. So the integral from 0 to 5 of e to the negative x should be proper. Certainly defined on the entire interval. Okay, the integral from 1 to 4 of 1 over x. Well, 1 over x is certainly defined everywhere between 1 and 4, so we're good to go. It's proper. We know for sure that this next one, the indefinite integral of 1 over x dx, is just going to be proper. Improper doesn't apply. Okay, for this next one, well, automatically seeing that infinity clues me into the fact that that integral is improper. If you're limited with one, that's all you have to say. See infinity, improper. See negative infinity, improper. That's automatic. And then lastly here, the integral from 0 to 4 of 1 over x is also improper because 1 over x is not defined at every point in the interval, specifically not defined at 0. This integral is definitely improper. And I'm going to even write here, this one is because f of x equal to 1 over x is not defined everywhere in the interval from 0 to 4. Specifically at 4. Hey, look, we're just talking about, you can grab one of those little handouts there, whether or not integrals are definite or indefinite or proper or improper. So when you're looking to see if an integral might be proper or improper, first of all, it has to be definite. Second of all, it has to either have an infinity or a negative infinity as one of its limits of integration, or it has to be undefined somewhere on the interval of integration. Often at the lower endpoint or the upper endpoint, but it could be somewhere in the middle. Okay, so let's do some, oh yeah, question. Part of the, like, if I was going to do one of these integrals with infinity?
Yeah.
Sure. Let's do them. So when you have an improper integral, one of two things can happen. The integral can diverge, which means the integral value doesn't exist, or the integral can converge to a value. So let's look at actually all the improper ones that were on my little list here. Let's start off with, sure, why not? Let's do the integral from 1 to infinity of e to the negative x. So what I would say about, actually, Co-17, so 17B, today is October 18th. This is a reminder, we're not going to have class on Friday. I'm not going to be in town. So I do plan, I think my plan is sometime between now and Friday morning to make a video kind of covering all the methods of integration we've talked about, because I think we're at a place where we've pretty much talked about every method of integration that is going to be accessible to us in this class. So that's kind of my plan. I'll certainly post an announcement once I have made the video and posted it. So that's the idea. And you should watch that video and mark attendance for Friday in that way. So whenever you have an improper integral, like this one, the first step, usually the first step, is to rewrite it so that you're dealing with the problem point in the interval of integration. So here, infinity is the problem. Infinity is always the problem. That's our problem. So we're going to rewrite this as the limit. Most people like to use a B for the upper limit, an A for the lower, although people use T or Z or whatever. You can really use any letter that you haven't already used. You shouldn't use X. Limit as B approaches infinity of the integral from 1 to B of e to the negative x dx. The rest of this process, except for like the very last step, is pretty much the same as you have done so far. You're just going to do the integral like you normally would, and then plug in the limits of integration like you normally would. And then at the very end, we're going to find the limit. So we're going to write the limit each time, but we're really just going to kind of ignore it. I'm really focused on what's happening inside these brackets. So we're going to anti-differentiate e to the negative x. And we're going to get e to the negative x divided by -1. But instead, since divided by -1 is the same as multiplied by -1, let's just write negative e to the negative x. From a lower limit of 1 to an upper limit of b. And then you're just going to plug in the limits of integration. We're still going to write the limit as b goes to infinity. And now we're going to get negative e to the negative b minus negative e to the -1. And then, after we've fully evaluated the integral and plugged in the limits of integration, now we have to ask ourselves, okay, what's the limit as b goes to infinity? I'm not great at e to the negative b. It's just not my favorite. I'm like, I would choose to rewrite this, although you don't have to. I would rewrite this as the limit as b goes to infinity of -1 over e to the positive b. And then I'm going to rewrite this too as minus is plus. Instead of e to the -1, I'll write 1 over e. So I think it looks nicer. As b goes to infinity, e to the b also goes to infinity. And 1 over e to the b is going to be super duper small. That's going to go to 0. So this is going to equal 1 over e, or e to the -1. And then the words we should write, or at least think about, is the fact that we should say that the integral from 1 to infinity of e to the negative x dx, it's okay to write that it's equal to 1 over e, but the more correct, and people will all the time, but the more correct thing to say is that this integral converges to 1 over e. But people are going to write that the integral from 1 to infinity of e to the negative x dx just equals 1 over e. I definitely saw in at least one of your professor's notes that they're just kind of like throwing infinities around haphazardly. That they're like, just do the integral and plugging in some infinities. And although that's fine, it's technically not the right way to do it. So I'm going to show you the way that's correct. And if your professor is allowing you to be a little bit more loose with things, that's okay. But I just want you to make sure, I want to make sure you've seen it the more appropriate way. I will say, as you move forward in mathematics, like if you get into higher class, people will often kind of just disregard. They'll be like, yeah, I know, I take the limit, but the limit's going to be the thing that I know I'm going to get. So I do kind of disregard that. But for now, we should be appropriate. Questions about any of this before we do more examples? My next example. Sure, let's look at my next improper one. So actually, this next improper one is the one people kind of usually start with, which is the integral from 1 to infinity of 1 over x dx. You've probably already seen this example in your class. We're going to do the same thing. We're going to replace the infinity with the limit. Actually, I should say, we're replacing the infinity with b. We're rewriting the integral as 1 to b of 1 over x dx. And then we're saying we're going to take the limit of that as b goes to infinity. And then it's the same thing we did before. We're going to integrate this. We're going to still have the limit out in front. The antiderivative of 1 over x is the natural log of the absolute value of x, evaluated from 1 to b. We plug in the limits of integration. So we're still writing the limit as b goes to infinity. Of the natural log. I'm not going to write the absolute values here. The natural log of b minus the natural log of 1. I didn't write the absolute values because both the things are already positive. 1 is certainly positive, and b going to infinity is also certainly positive. It's also perfectly fine to write the absolute values there if you want to. Natural log of 1 is 0. So this is going to equal the limit as b goes to infinity of the natural log of b, which is going to be infinity. If you think about the graph of the natural log. Ooh, I've told somebody this. Everybody look at your right hand. My right hand is not good for this because I am old and have lots of lines. But you all are young and have less lines on your hands. So your right hand, if you're right-handed, put down your pencil and look at your right hand. Right there is a pretty nice e to the x graph. Right there, although again, not great on my hand, is a pretty nice natural log of x graph. So if you're ever like, what does e to the x natural log of x look like? If you're right-handed, which many of you are, set down your pencil, look at your right hand, be like, oh yeah, e to the x, natural log of x. So natural log of x looks like this. It's got an intercept at 1, 0. It's got a vertical asymptote at the x-axis, y-axis, holy smokes. And importantly, in this context, as the x values get larger and larger and larger, the y values also get larger and larger and larger. So this limit certainly is infinity. What does that mean? Well, it means a couple things. It means the integral from 1 to infinity of 1 over x dx diverges. It also means the area under this curve from 1 to infinity is infinite. So if you actually draw this, which I know I'm squeezing things in here, which is never my favorite thing to do. But if you just draw this, even though, right, we definitely are getting an infinite amount of area there. Whereas this function, e to the negative x from 1 to infinity, if you draw that one, well, e to the negative 1 is pretty small. It does something similar, but it gets small fast enough so that the area under that curve ends up being finite. So both of these graphs have kind of a similar, like if you graph these better than I have on Desmos, and you look at them, they both look like, well, they're doing the same kind of thing. But this one has a lot more area under it than that one. How do we know? We did the integrals. We saw that, oh yeah, this area is getting larger and larger and larger and larger. This area here is getting closer and closer to 1 over e, which is a pretty small number. It's like 0.3 approximately. Do we have to know that geometric interpretation? Not really, but it's good to have a sense of what's happening. Okay. If you have questions, you should ask them. I try to not ask, does anyone have any questions, but I fail pretty hard at that usually. So if you have questions, you should ask them. Let's look at the last one that was on my list here. So I'll point out this last one on my list, bless you, from 0, the last improper one on my list. We should be smart, meaning we shouldn't repeat work we've already done. We already know what the integral of 1 over x is. It's the natural log of the absolute value of x. So, I mean, that one's pretty easy. We probably don't, it's not so much work, but we should think about the fact when we do this. So this 1 over x is undefined when x is equal to 0. So 0 is the problem, not infinity. There isn't an infinity. That's our problem. Whatever point is the problem, meaning whatever point makes the function undefined, that's the one we're going to replace with an a or a b. Usually a for lower, usually b for upper. But again, whatever you like. So I'm write this as the integral from a to 4 of 1 over x dx. I'm going to take the limit as a approaches 0 from the right. Why from the right? Well, if I'm doing the integral from 0 to 4, if I'm between 0 and 4, what side of 0 am I on? The right side of 0. So when your improper integral is one where it's not an infinity or a negative infinity negative infinity that you're dealing with, but a 0 or a 5 or a 2 or a real number, it is usually considered good practice to also say which side you're approaching from. And it really just depends on if it's the lower limit, you're approaching it from the right because you're bigger than it. If it's the upper limit, you're approaching it from the left because you're smaller than it. It's usually not that hard to figure out which way you're going. All right, so same deal. We integrate this. We get the limit as a approaches 0 from the right. It actually is, that's not that. The antiderivative of 1 over x is still the natural log of the absolute value of x. From a to 4, we plug in, we get the limit as a goes to 0 from the right of the natural log of 4 minus the natural log of a. Again, you will notice I didn't write absolute values because 4 is positive and a is also positive, so I didn't need to, but I could have. Okay. As a goes to 0, what happens to the natural log of a? It's really good to have the concept of what the graph of natural log looks at for most of these things. So if we look at the graph of natural log again, where here is x equal to 1, y equal to 0, as my x values get closer and closer to 0 from the right, what are my y values doing? Yeah, down, 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 down to negative infinity. This one also diverges. It's going to be equal to the natural log of 4 minus negative infinity, which is the natural log of 4 plus infinity, which is infinity. So this one also diverges. Yeah. I would say when the integral has an infinite, it has a value that isn't finite. So it could be that, so what I should be saying, so if we look at the actual graph of the function, here's what we're looking at. So if x is 1, y is 1. If x is 2, y is a half. 3, y is a third. 4, y is a fourth. But if x is really small, my graph is getting infinitely large. So my graph looks like this. And I'm stopping right here at 4. Oh, that's a 1. That's not 0, James. Come on. So I'm trying to figure out how much area is under the graph from 0 to 4. So I'm looking at all this. And that area, according to our calculations here, is infinitely large. We're getting an infinite amount of area. We're using the graph of the natural log to help us determine that when we evaluate the integral, but we really are getting a positive infinity because we're getting a minus infinity. So our area is divergence. Sometimes you can diverge, and sometimes people will ask, does the integral diverge to infinity, meaning you have a positive infinite amount of area, or does it diverge to negative infinity? And sometimes the answer is you can't tell, actually. You can say positive, negative, or sometimes it's inconclusive. Other questions? Okay, let's look at some more examples. Yeah. Sure. Let's look at the integral from, yeah, let's do that one. Negative infinity to 0 of x over 1 plus x to the 4th dx. Certainly improper. We're going to write this as the limit as a approaches negative infinity of the integral from a to 0 of x over 1 plus x to the 4th. I should point out, when your limit is at a approaching negative infinity or b approaching infinity, you don't have to say you're approaching infinity from the left. There's only one side you can approach infinity from, the being less than infinity side. Likewise, we never say we're approaching negative infinity from the right, because it's never a question. Integral of x over 1 plus x to the fourth. I think I'm gonna have to do a u sub. So here's what I would say. If your integral requires more complicated processes than just like finding the antiderivative, like you have to do a u sub or integration by parts or partial fractions, I don't want to write all of this machinery in the 3 or 4 or 5 or 6 steps I'm going to do. So here's what I would do instead. Let's do the indefinite integral. Let's find the integral of x over 1 plus x to the fourth. And I think this is usually the better way to do it. I would say you generally, in my opinion, and some people might differ, you don't usually want to do a u sub and change your limits of integration when it's improper like this. It always feels a little bit dicey. So I would encourage you to do what I'm about to do. What's a good choice for you here? Well, you might start by trying 1 plus x to the fourth. It's not a bad idea. It's not the right choice, though. And the reason it's not the right choice is because if I find my du, well, the derivative of x to the fourth is 4x cubed, and then I slap on a dx. And I don't have a 4x cubed or an x cubed times dx. The 4 I don't worry about, but I don't have an x cubed times dx. So that's kind of problematic. Say that one more time. I mean, that is x is x over 1, but the issue here, or x to the 1 even. But the problem is I'm looking for an x to the third. And I can't really make that happen in any sort of reasonable way. I could, like, if I really wanted to, although I'm not going to because I know it's not going to work, I could multiply like by x squared on top and x squared on the bottom. Then I've got an extra x squared on the bottom. It just seems like, here's the choice that you actually need to make here. And it's not super intuitive the first time you learn it, but the actual choice we're going to make is to let u equal x squared. There is actually 2 good reasons for this. The better reason, the most important reason, is the derivative of u is showing up. I do have an x times dx in my integral. That's a good sign. So I'm going to rewrite this as 1/2 du is equal to x times dx. And when I start rewriting my integral, that's the part I'm going to worry about first. I'm always worried about making sure that this transforms into something with du. The rest we can fix. So now I'm going to write something that's kind of wonky. That's fine. I'm going to write this as a mixed, meaning it's going to have u's and x's in it. 1/2 du over 1 plus x to the fourth. But instead of writing x to the fourth, I should write x squared squared. Do I need a dx? No, I already dealt with dx. It turned into du, and I wrote du, so I'm safe. Should I write this integral at all? Really? Probably not, but fine. Who cares? So then x squared is equal to u. So I can rewrite this as, let's put the 1/2 out in front, the integral of du over 1 plus u squared. Or if you like, 1/2 the integral of 1 over 1 plus u squared du. And that is an integral that we're supposed to memorize. What's the antiderivative of 1 over 1 plus u squared? Arctangent of u. This is equal to 1/2 arctangent of u. I'm not going to write the plus c because I don't need it right now, which is going to be 1/2 arctangent of x squared. Great. Did all my side work. Now let's get back to the actual problem. We're dealing with this. So the limit as apologies, goes to negative infinity of the integral from a to 0 of x over 1 plus x to the fourth dx. I just figured out that the antiderivative of x over 1 plus x to the fourth is 1/2 arctangent of x squared. So I'm just going to jump to that step and not write any of this trash. I mean, I know I already wrote it all, but you know what I mean. I'm not going to write it with the limit stuff. So now I'm going to have the limit as a goes to negative infinity of 1/2 the arctangent of x squared evaluated from A to 0. And I think once you get comfortable with this, it's actually perfectly fine to actually skip this step and jump straight to writing the limit as A goes to whatever of 1/2 arctangent of your first value plugged in. Oh, come on, you can fit. Minus, sorry, it's terrible. 1/2 arctangent of A squared. What's the arctangent of 0? What's the angle that if you take tangent of that angle, you get 0? It is 0. What's the arctangent of 1? Tangent of what angle equals 1? It's pi over 4. Right? Sine pi over 4 is root over 2, cosine pi over 2, so tangent is 1. So the arctangent, right, says whatever the number you're inputting is, I want you to tell me the angle that if you take tangent of that angle, you get the value that we're looking at. So the arctangent of 0 is 0. So we've really got the limit as A goes to negative infinity of negative 1/2 arctangent of A squared. Okay, now here's the thing that's kind of funky. As A goes to negative infinity, A squared goes to positive infinity. So this inside part is getting larger and larger and larger for the whole inside part. And then the arctangent of positive infinity is, that's the final answer almost. It's pi over 2. So here's, and this probably seems like, why would it be pi over 2? We'll come back. Well, let me write the final answer and then we'll talk about the why. It's gonna be negative 1/2 times pi over 2, which is negative pi over 4. So this integral converges to negative pi over 4. It definitely makes sense that it's negative because if you were to graph the original function on the left side over here, we'd have negative values. It would be all under the x-axis. In fact, let's graph it. Not very well. But if I actually wanted to graph, can I move papers around here in a seemingly logical way? Maybe. Just so you all can see it, f of x equal to x over 1 plus x to the 4th looks kind of like this. Sure. Has an intercept at 0, and then kind of does this deal. So certainly the area from negative infinity to 0 is getting counted as negative because it's all under the x-axis. Whereas if I had done the integral from 0 to infinity, it would have been positive pi over 4. And if someone said what's the integral from negative infinity to infinity, it would be 0 because the left-hand part and the right-hand part would cancel each other out. It's an odd function. Okay, but why this? Why does the limit as A approaches infinity of the arc tangent of A equal pi over 2? And the reason I bring it up is because you're probably going to get asked it at some point. Well, let's talk about tangent. Tangent has vertical asymptote to every odd multiple of pi over 2. So here's what one period of tangent looks like. I'm not going to draw the rest. I'll point out that that's pi over 2. That's negative pi over 2. If you plug in pi over 4, tangent to pi over 4 is 1. If you plug in negative pi over 4, tangent to negative pi over 4 is negative 1. So I'll point out tangent of pi over 4 equals 1 is equivalent to saying the arc tangent of 1 is equal to pi over 4. That's what inverse functions do. They undo what the other one does, or they switch the role of the input and the output. For this function, the input's pi over 4, the output's 1. For this function, the input's 1, the output's pi over 4. So if I said the tangent of pi over 3 was equal to the square root of 3, you could also tell me that the arc tangent of the square root of 3 was equal to pi over 2. All right, so now check this out. If my angle gets really, really close to pi over 2, tangent of something really, really, really close to pi over 2 is going to be really, 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 really big. So tangent of almost pi over 2 is big. Or if we reverse those roles, the arctangent of something big is almost pi over 2. That's why this is what it is. The other reason, the more graphical reason, is because if you actually graph the arctangent, when you find the inverse function, you reflect the graph across the line y equals x. If I take this graph and reflect it across the line y equals x, instead of getting vertical asymptotes at pi over 2 and negative pi over 2, I get horizontal asymptotes at pi over 2 and negative pi over 2. And this graph ends up looking like this. And you can see, oh yeah, as x gets larger and larger and larger and larger and larger, the graph gets closer and closer to what? Everybody? Pi over 2. Right, that horizontal asymptote is the value of the function is getting closer and closer to. So I probably shouldn't say anything more about this because it's not like the biggest deal ever, but we kind of got stuck on the road. So, but yeah, so when you take the limit of arctangent, it's not infinity, it's pi over 2. Okay. Kind of weird, I know. It's a little strange. Let's look at some more normal examples. Unless there's any questions about this, I'm happy to answer any questions if there are questions. It's kind of like how the e to the x and the natural log of x are inverse functions, and they are reflections of each other across the line y equals x. The same thing is true here. If you reflect this graph across the line y equals x, it's going to look like that graph. All the x things become y things, all the y things become x things. Let's look at a few more examples here. Let's say we had the integral from 1 to 9 of 3 over the cube root of x minus 1 dx. I will point out it is really easy to do this problem without using limits, and it's just not as right as it should be. You could totally do this problem and get the right answer without using the limit, but technically that function is undefined at what value of x? 1. So I really should write this as the limit as x approach, sorry, not x, I should use anything but x, as a approaches 1 from the right of the integral from a to 9. And I would encourage you to rewrite this. Instead of writing it as 3 over the cube root of x minus 1, I would write it as 3 times x minus 1 to the negative 1/3 power. I'll probably even bring the 3 out in front, to be perfectly frank. Yeah. Yes, because if we're so our interval of integration is from 1 to 9. So we're integrating over this interval. And if we're between 1 and 9, which side of 1 are we on? The right side. It's easy if you draw a picture. You're like, oh yeah, of course, I'm on the right side of 1. So then we could do a u sub here, but it's such a small, right? U equals x minus 1. I feel like we don't need to write out, right? You're really just going to get u equals x minus 1. Your du is going to equal dx. And the integral of u to the negative 1/3 is just reverse power rule. So we're going to get the limit as a approaches 1 from the right 3 times. Okay, here's my u to the negative 1/3 plus 1 divided by the same new power. But instead of writing u, I'm going to write x minus 1. If your u is just x plus something or x minus something, you can just kind of do this as is and not really do the u substitution. Evaluated from a to 9. Let's do 2 things at once here. Let's both write the limit. That's not one thing. Let's simplify this by saying 3 times 3 halves is 9 halves. And actually plug in the 9 and a. And be careful, if you're sloppy like me, make sure your 9 looks very different than your a. Or maybe choose a different letter. So plugging in 9, I'm going to get 9 minus 1 to the 2/3 minus plugging in a, I'm going to get 9/2, or you could put parentheses if you wanted to. A minus 1 to the 2/3. Simplify, well, actually, now I should take the limit. So if I plug in 1, I'm going to get 9/2 times 8 to the 2/3 minus 9/2 times 0 to the 2/3. And 0 to the 2/3 is perfectly fine. 0 to a positive power is just 0. So we're going to end up with 9/2 times 8 to the 2/3, which is 9/2 times 8 to the 1/3 squared, which is 9/2 times 2 squared, which is 9/2 times 4, which is 18. So this thing converges to 18. And there are other ways of dealing with 8 to the 2/3, but I think the easiest way is to do the root part first and the power part second. Okay. So does this integral converge or diverge? Give me a no, it's hard to make a C or a D. Who says converge? So thumbs up for converge, thumbs down for diverge. Yeah, definitely converges. To what? 18. All right. Oh, yeah, we should do one of those for sure. Okay. Let's look at something else here. Sure. Let's say we have, yeah, that's annoying enough to do. Let's look at the integral from 2 to 7 of 4 over x minus 5 to the 3rd power. Yeah. Oh, I don't see anything, but if someone had a question on Zoom, pipe up. Anybody?
I had a question about the previous page. Do you still have it?
Say that one more time.
Do you still have the previous page? I had a question about it.
No, I threw it. No, of course I did. I didn't throw it in the trash. Yes, what's your question?
So on the second part of the equation, it's 9/2 to the 8 and then minus 9/2 to the 0. How come it became 0?
So it's not 9/2. So it's 9/2 times 8 to the 2/3 minus 9/2 times. So what I did was I'm taking the limit. So I guess I could, let me show one more step here. If I actually take the limit here, I'm getting 9/2 times 9 minus 1 is 8. Sorry, 9/2. And then minus 9/2 times, and to take a limit, the first thing we always try when we take a limit is just plugging in what the limit's approaching. So I'm just plugging in 1 for A and getting 1 minus 1 to the 2/3. And then 1 minus 1 is 0, and 0 to a positive power is still 0. That's what's happening there.
Thank you.
You're welcome, of course. Thanks for catching that. I appreciate it. Definite or indefinite? Definitely. Definite. Proper or improper? Improper. Where is that function undefined? Show me on your fingers. Show me on your fingers. What? Yes, this many fingers. That function is undefined at x equal to 5. Okay, let me ask you. Proper or improper? Proper. Where's that function undefined? 5 still, but 5 is no longer in the interval of integration. I should have asked one like this on the first sheet too. Oh well, I wasn't thinking about that. So this integral is definitely proper. You could do this straight away, the easy way, meaning you would just anti-differentiate and plug in the values. In fact, if we did this, it would be the integral from 8 to 10 of 4 times x minus 5 to the -3rd. We would anti-differentiate. You would get 4 times x minus 5 to the -2 divided by -2 from 8 to 10. I would probably rewrite this as -2 times 1 over x minus 5 squared from 8 to 10, and then just plug in, and you would get -2 times 1 over 10 minus 5 squared minus 1 over 8 minus 5 squared. I don't really care what that is. I just wanted to point out that that would be a proper integral. There's no places where the function is undefined on that interval, so no worries. But as you have noticed, it's easy to miss an integral being improper if the place of impropriety, I don't know, if the place where it's improper is in between the limits of integration. And the extra annoying piece of this is that to deal with it, you have to break it up into two integrals, where the place of problem is one of your limits of integration. So I'm going to break this up as the integral from 2 to 5 of 4 times x minus 5 to the negative third, plus the integral from 5 to 7 of 4 times x minus 5 to the negative third. How terrible. Not that bad, really. When you have something like this where you have to break it into two or more pieces, I highly recommend dealing with each piece individually, because here's the story. If the integral diverges, I should back it up. If one piece diverges, the whole thing diverges. If all the pieces converge, then the whole thing converges. So I would do a piece of piece. I'm going to do the first piece, and if it converges, then I'll do the second piece. And if it converges, then the whole thing converges. But if I do the first piece and that one is divergent, stop. You're done. The whole thing diverges. That's it. So let's look at this piece first. So I'm going to look at this. I'm going to say that's going to be the limit. Oh, yeah, sure. Yeah. As A approaches 5. Sorry, B approaches 5. It's the upper limit, not the lower limit, although you could use A if you wanted to. Of the integral from 2 to 5 of 4 times x minus 5 to the negative third. Okay, let me ask everybody, if I'm between 2 and 5, I'm approaching 5 from which side? The left. Because I'm between 2 and 5. Am I less than 5 or bigger than 5? Definitely less than 5 if I'm between 2 and 5. You can always draw the little picture, right? 2, 5, I'm living in here. Oh yeah, I'm definitely left of 5. And then we already did the antiderivative. Great. The limit as B approaches 5 from the left. The antiderivative, I'm going to write it as negative 2 over x minus 5 squared. And I really will recommend, it's usually best to try and write your antiderivative simplified with positive powers. And I'll tell you why in just a minute. I'm evaluated between, oh, wow, I made a mistake. It's not a huge mistake. I can easily fix it. But I did make a mistake when I wrote this integral. What did I write? I don't know. Can someone tell me what I did wrong? That's what I did wrong. That should have been a B there, not a 5. Because I'm replacing the 5 with B because 5 is a problem. And I'm saying, oh, I can do the integral just fine. It's totally fine to plug in B because B isn't 5. It's approaching 5, but it's not 5. So then I can rewrite this as the limit as B approaches 5 from the left of negative 2 over B minus 5 squared minus negative 2 over 2 minus 5 squared. Okay, so if I plug in B equal to 5, what's 5 minus 5? Oh, geez, excuse me. 5 minus 5 is 0. 0 squared is 0. And division by 0 is a bummer. It means the function, or means the integral diverges. So this part here means we're going to get division by 0. So we're going to diverge. Now, I could be a little bit more specific. Technically, I'm getting the limit as B goes to 5 from the left, negative 2 over B minus 5 squared. I'm going to rewrite this as plus 2 over 9. I don't really care. My numerator is negative. My denominator is slightly a negative number squared, which is positive. So technically, this is diverging to negative infinity. But here's the thing. This diverges because one piece diverged. The other piece could converge, could diverge. I don't know. I don't really want to know. But the problem is, if someone asks you how it diverges, which I don't think most people are going to be asking, but occasionally there's like one professor who asks questions like, does this diverge to infinity? Does this diverge to a negative infinity? Does this just diverge overall? To actually be able to tell what it diverges to, you have to look at the other piece, which is annoying. I will point out this other piece actually does diverge to positive infinity, which means the overall divergence can't be discerned. Because negative infinity plus infinity could be anything. It's an indeterminate form. It's like 0 divided by 0 or infinity divided by infinity. It's something that could be anything, so we can't say what it is. So this one, we wouldn't be able to say if it diverges to infinity or negative infinity, it just diverges. What time is it? Okay. The reason I'm saying you should write it like this is because if you write it like this, so if I wrote it as the limit as b approaches 5 from the left of -2 times x minus 5 to the negative second, and then actually plugged in b and 2 and got the limit as b approaches 5 from the left of -2 times b minus 5 to the negative second minus -2 times 2 minus 5 to the negative second. It can be really easy to convince yourself that this is 0. What's 5 minus 5? What's 0 to the negative second? It's not 0. It wasn't 0 there. Why would it be 0 here? 0 to the negative second. That's why you shouldn't write it like this, because it's really easy to think it's 0. But 0 to the negative second is really 1 over 0 squared. What's 0 times 0? What's 1 divided by 0? That's a problem, right? That does not exist. So be careful. 0 to a positive power is just 0. 0 to a negative power is undefined. It's division by 0. It's just hiding. So don't let that division by 0 hide from you. Write your powers as positive powers so that you're not going to be ending up in that kind of weird place. Cool. Oh, we should do, yeah. Sorry. Let me throw one more at you real quick here, just because we should see one more. Let's say we want to do, sure. The integral from 0 to infinity of x squared e to the negative 5x dx. That looks like trash, but we should at least rewrite it as the limit as b goes to infinity of the integral from 0 to b of x squared e to the negative 5x dx. And here's where the thing I said before about not writing the limit and the inner limits of integration and all the steps really applies. If you were going to do this integral, what method would we need to use? By parts, twice actually. How fun. So we're going to do that, but we're going to do it fast because this is one of those special ones where you can say u is x squared and then take all the derivatives. dv is kind of terrible. It's e to the negative 5x, and then the antiderivative is negative 1/5 e to the negative 5x, and then the antiderivative is positive 1/25 e to the negative 5x, and the antiderivative is negative 1 over 125 times e to the negative 5x. Woo! So then it's plus this times this, minus this times this, plus this times this. And I can see that all the signs are going to end up being negative because it's plus that times a negative, minus that times that, plus that times a negative. So they're all going to be negative. So I can see that we're going to get this is equal to the limit as b goes to infinity of my integral, which is going to be terrible. It's going to be negative 1/5 x squared e to the negative 5x minus 2x over 25 times e to the negative 5x minus 225 times e to the negative 5x from 0 to b. And I don't think you're required to know L'Hopital's rule for this class. Normally you would do this using L'Hopital's rule, but we're gonna skip that because we only have like here's what you should do. Factor out the e to the negative 5x, right? This is the limit as b goes to infinity of e to the negative 5x times negative 1/5 x squared minus 2/25 x minus 225. And then actually write this as the limit as b goes to infinity of the top thing, negative 1/5 b squared minus 2/25 b minus 225 over e to the positive 5b. I know I'm doing a simplification and plugging in at the same time. Forgive me. Minus, if I plug in 0, I get 0 minus 0 minus 2 over 125 over e to the 5 times 0. And here's the point. This quotient here, the top is a polynomial. It's b squared plus a something times b squared plus something times b plus a constant. The bottom thing is an exponential. Which thing grows faster? The exponential grows faster. So this is going to outpower that by a long shot. Or in other words, the denominator is much, much, much larger than the numerator, which means the fraction is getting very, very small, right? The top is like 1,000, the bottom's like a bajillion. And 1,000 divided by a bajillion is tiny. So that's going to go to 0, and you're going to be left with positive 2 over 125 divided by 1. So that's how you should deal with something like this. Again, you're doing the limit or the integral without writing all the crap. And then after you do the integral, then you do the limit of the rest and try and figure out what's going on. All right. I won't see you all on Friday.